We are beginning section 5.2 on the definite integral. Here's the schedule. Again, moving into definite and indefinite integrals. So finally, we're going to get to integrate sort of. I might have mentioned, last time sometime that we're taking the long way around. The most general definition of the area of a region that lies under the graph of a continuous function, notice that word continuous, is the following. We have a is equal to the limit as n approaches infinity, and then you have your summation, I is 1 to n, of f of x sub I delta x. So f of x sub I is the function value for a particular rectangle, and that represents the height of that specific rectangle. Delta x, remember, is the width of each rectangle, and the width of each rectangle is the same while the heights will differ. Once we calculate the area, so height times width for each rectangle, then we add up all the areas, that's our summation, and then we take the limit as the number of rectangles grows arbitrarily large. This is the most general definition of area under a region, and it's not an approximation, it's an exact value. That definition, the limit of the sum of all the areas as the number of rectangles gets arbitrarily large, that is the definition of the definite integral. The entire definition of the definite integral in all its full glory. We have a function which has to be defined on some interval, including those endpoints. And then if we divide that interval into subintervals, n subintervals, so we're getting set up for those rectangles, and each of those subintervals is of equal width, so delta x, remember that's going to be the width of your rectangle, is equal to b minus a, so upper bound minus lower bound divided by n, that'll give you the width of each rectangle. So the definite integral of f from a to b is this integral symbol from a to b, f of x dx, and that is equal to the most general definition of the area. So provided this limit exists and gives the same value for all possible choices of sample points, if it does exist, we say that f is integrable on this interval. If we just dissect all the symbols, f of x on the left there is called the integrand. That elongated S shape is called the integral sign, and thank you Leibniz for that notation. A and B are called the lower and upper limits respectively. And then the precise meaning, if you stare at that, the precise meaning below within the absolute value signs, what is that really saying? That is saying that the definite interval minus the approximation of an not the definite interval, the definite integral minus the approximation of the area under the curve is less than some epsilon. So there's some error factor between the actual area, which is the definite integral, and the approximation given by just adding up the areas of all the rectangles. And oh, by the way, this sum of the area of the rectangles, this particular sum has a particular name called the Riemann sum. And if f is greater than or equal to 0, then this Riemann sum is the sum of the areas of all the rectangles. And compare that to the integrals. If f of x is greater than or equal to 0, then that integral is the actual area under the curve. So in one case, you have the sum of the areas of the rectangles, which you've tried to fit into that curve, and On the right-hand side, you have the definite integral, which is the actual area under the curve. Be aware of net area. So the curve, not all curves are going to stay above the x-axis. When they dip below the x-axis and you're trying to find the area, whether you're taking the sum of the rectangles, the areas of the rectangles, or whether you're using the definite integral, you will have some areas which are negative. And of course, these are going to be subtracted out of the areas which are positive. So you end up with a net area. If you wanted the actual true geometric area, you would have to adjust for the negative areas. But right now we are calling this the net area.